Hi, kids. All right. We have another conservation momentum problem, another collision. In this case, we have a 200-kilogram bumper car is moving 4 meters per second east. It collides with a 250-kilogram bumper car moving 3 meters per second west. And after the collision, I'm going to tell you that the 200-kilogram car is moving west with a speed of 1 meter per second. I want to know the other car's after velocity. And then we also want to figure out, is the collision an elastic collision? Okay. So again, let's first sketch what's going on. So I have my 200-kilogram car moving this way, and then my 250-kilogram car moving this way. This is my before picture. And then after my 200-kilogram car is moving that way, and I want to figure out what happens without. Okay, so there's my picture. So before, after. Remember, conservation momentum means your total momentum before has to equal your total momentum after. So what that means is the m1v1 plus m2v2 must equal m1v1 plus m2v2. Okay, or this is going to be my after. Okay, so now let's plug some numbers in. And then again, the whole point of making pictures here, guys, is that if you draw a picture, you should hopefully realize this is going east, this is going west, so I have to, change my direction. And since we've been typically calling this way positive, this way negative, we'll stick with that. That's a good idea. So that this is 200. This will be positive 4 plus 250. This is going to be negative 3. Equals, okay, everybody see where I'm going to get my numbers, 200 times, again, this would be negative, times negative 1, plus 250 times V2. Okay, so then I got to do the math, 800, 750, so this is going to be positive 50 kilogram meter per second. This is negative 200, so I bring this over here, so negative 200 plus 250 V2, and do the math, and you get, so 250, oh look, 250 divided by 250, woo! So you end up with, so V2 equals positive 1 meter per second. So let's talk about what this means. This means that it is going east, because it's positive, and that's my velocity. So it's positive 1 meter per second. So it would go that way 1 meter per second. So now I need to decide, is this an elastic collision? So to determine if it is an elastic collision, well then you have to realize, oh, elastic collisions, kinetic energy is conserved. So I'm going to erase this since we already did the momentum. Now we're just going to figure out, is kinetic energy conserved? So kinetic energy is 1/2 m1 v1 squared plus 1/2 m2 v2 squared equals, so 1/2 mv squared and 1/2 mv squared. Okay? And then plug my numbers in. Now remember, energy does not have directions, so I don't have to worry about pluses and minuses. And as it turned out, it's squaring it anyway, so it wouldn't really matter. But if I go 1/2 200 times 4 squared plus 1/2 250 times 3 squared equals 1/2 200 times 1 squared plus 1/2 250 times 1 squared. And if you do the math on this side, you're going to get 16 times 100. So I get 1600. And then here I get 9 times, that one I can't do in my head. So 9 times 125 is 1125. Okay, so on this side, I get a total of 2,725 joules. On this side, I'm going to get 1 squared. This is going to be 100 plus 125. So obviously 225 joules. Obviously, this is not a perfectly elastic collision because I lost a bunch of kinetic energy. And then if I wanted to figure out how much energy was actually converted to heat in this collision, you would say, all right, well, this minus this was converted to heat. So it looks like there is 2,500 joules of energy converted to heat. Bye, kids!